Section 9.1 is about comparing proportions from two different but related groups. And really, the comparing groups idea is kind of the overall thing of Chapter 9. So in Chapters 7 and 8, when we went over confidence intervals and then hypothesis testing, it was always for one group, so you just had one quantity. So just a single proportion or a single mean. In both cases, right? Chapter 7 for confidence intervals and Chapter 8 for hypothesis testing. But now we're going to have two proportions where it's going to be essentially comparing two different but somehow related groups. And this would make sense just like for a single proportion when you have categorical data. And the check to make sure you have a big enough sample size, or I guess big enough sample sizes since you'd have two of them, it's right here, where it's the same concept that we had before, it just happens twice. There is one slight difference, which is that when we did this before, like for a single proportion, for a confidence interval, we would have used the sample proportion as part of the check, but then for the hypothesis test, we could use the value in the null. Here you can't do that because there aren't going to be specific values in the null for P1 and P2, so you just have to do it the confidence interval way all the time. So it's just always using the p hats because there's no value from the null that you could sub in for P1 and P2. What you end up with for the null is that P1 equals P2 or P1 minus P2 equals 0. And all that says is that they're the same, but it doesn't actually specify what they are. So there's nothing that you can sub in. So other than that one little tweak, it's still the same idea of you want the number of successes and failures to both be at least 5, right? It's still going to be that overall idea. And you just have to do it twice because you got two groups. All right, then the confidence interval formula, it's still going to be the same general setup. So the general setup is right here, where it's point estimate plus or minus the critical value times the standard error. But the point estimate and the standard error, especially the standard error, are going to be a little more elaborate now. So the point estimate, I guess this part kind of follows naturally because you think, well, generally if p hat is the best point estimate for p, then let's say if you have two population proportions, P1 and P2, your best estimates are just going to be the respective sample proportions. So like P1 hat would be your best point estimate for P1, P2 hat's your best point estimate for P2. So like it says in that first bullet point, the natural point estimate for P1 minus P2 is P1 hat minus P2 hat. All right, that part makes sense, right? It's a little more complicated than before, but it makes sense that that's what it would be. Critical value, use the standard normal distribution, so that still holds up. Anything that involves proportions, whether it's confidence interval, a mean, or two proportions instead of one, you still use the standard normal. So it's still going to be 90% confidence, your critical value is 1.645, 95% is 1.96, 99% is 2.576. Same ones that it was before, so that's nice. Especially because if you're going to do things by hand, the standard error would create a whole bunch of work. You can get around this if you use StatCrunch, but if you want to do it by hand, this looks like a lot, right? I mean, looking at that root right there, it looks like there's a lot going on. Like if you were going to have to put that into a calculator, you have to kind of think about how you're going to put everything in before you actually do it. All right, well, why is it so huge? Because there are two sources of sampling variability to account for, one from the first sample and one from the second sample. So if you look at those two quotients underneath the radical, they basically look like what you would have for a single proportion. Like each one does. So like the first one looks like if you were just trying to estimate P1, the second one looks like what you'd have if you were trying to estimate P2. But if you're trying to estimate both, or I guess really you're trying to estimate the difference between P1 and P2, both of those sources of variation are going to be in play. So under the radical, you get both of them. So that means that if you were going to do all the algebra yourself, you get this huge radical. And then putting it all together, that's what the confidence interval would look like at the very end. And yeah, it's a bit of work if you're going to do it by hand. Although I guess if you were going to do it with your calculator, like if you're going to do the standard error, I would do everything under the radical first and then take the square root of the previous answer. And that should work out correctly. As long as, I guess, maybe if you simplified the 1 minus P1 hat and 1 minus P2 hat before you put it all in, I would probably do that. But it's doable, but I mean, it's a little bit of work. All right, then what about the hypothesis test? So the null is that the population proportions are the same. So it's always that. That's always going to be your null. So it's always going to be this. That P1 equals P2 or P1 minus P2 equals 0. Sometimes you see it phrased one way, sometimes you see it the other, but those are equivalent statements, right? If you started with P1 equal to P2 and subtracted P2 from both sides, you get P1 minus P2 equals 0. And then just like with the single parameter test, you've got 3 options in the alternative for what kind of inequality you can have. It's most common that you would get the not equal to. So then basically your null is that the population proportions are the same, and then the alternative is that they're different. But sometimes you can have the one-sided alternative if you want to look for evidence that P1 is bigger than P2 or P1 is smaller than P2. Then that's what you would use the one-sided alternatives for. And yeah, you see them once in a while. But the most common one I would say is definitely the two-sided alternative. The test statistic, it's the same general setup as before. So sample measure, which I guess here would be P1 hat minus P2 hat, minus the null value over the standard error. The null value is 0 because, so basically it's this right up here. It's that version of it. That's where you get that the null value is 0. Because then P1 minus P2, if you're viewing that as the parameter, then that's what the null hypothesis says it's 0. So then the test statistic would be computed under the assumption that that's true. So right, you're going to sub your null value right in there. But then that doesn't really give you a thing that you can sub in directly into the standard error, like what we would have for a single proportion test. So what you do instead is that when you compute the standard error for the hypothesis test, you use a pooled sample proportion. So by pooled, that just means that rather than having the two samples completely separate, which they are in actuality, if you're assuming the null is true and there's just one population, then you could just shove them together and have one giant sample. So that's basically what you do. So right here, this is the pooled sample proportion, where if P1 hat's got some numerator and denominator, so I just said x1 and n1, and then P2 hat is x2 over n2. Then if you pool them together, you would combine the sample sizes and then just add the number of successes. So basically you add the numerators and add the denominators. And that would do it. And then you end up with a standard error where you have the two numerators being the same thing. And that's the best that you could come up with for taking care of that assumption that the null is true, right? Because then that way you effectively have the same value that you're subbing in as an estimate for P1 and P2 when you use that pooled proportion, right? Rather than having a separate P1 hat and P2 hat, which would probably be different numbers. All right, so then the test statistic, it looks like this. Usually I would say most people write it this way, and then it's just kind of understood that the numerator is P1 hat minus P2 hat, then minus 0, and the minus 0 is usually just left out. So that delta 0 right here, that's there really just to imply that it doesn't have to be 0. You could have something else, but realistically it's going to be 0. So delta 0, like the delta just, as I guess an abbreviation for change or difference. Usually that's going to be 0. I mean, you could use other stuff though, so I did kind of generalize that rather than just writing it as a 0. But for what we're going to do, it's just going to be a 0. And that's by far the most conventional thing to do. So let's see. Then you would use the standard normal distribution to get the p-value just like before. And if you were going to use StatCrunch to grind out all the algebra, basically you would do everything except I think I have a little error here. That should not say 1 sample. That should say 2 sample. All right, so I got to go back and fix that. Because if you got 2 samples, you want to pick that option. So if I go to StatCrunch, I can show you where it is. So stat, then proportion stats, 2 sample, and then we're never going to have data for proportions. We're always going to have the sample proportions. So you would just go to with summary. And then you can see in here, you've got a place to put your first sample proportion, it's numerator and denominator, then second sample proportion, numerator and denominator, and then whatever you're going to do, a hypothesis test or a confidence interval, all that stuff right there. You can toggle or change whatever you need to do. All right, so let's see. This first example, we've got that in a study about nightmares, 160 men, 192 women were sampled, and each individual indicated if they have nightmares often or seldom. And then, I guess, first things first, why can we apply the central limit theorem? Because the numbers of successes and failures are all at least 5, right? So the numbers of successes are the often column, they're the ones in bold. And the failures, I guess, would be seldom because we're interested in often, right? So seldom just being the other possible choice here, not the bad one, right? I would argue that's the better one here. But the 55, 60, 105, and 132, so the two numbers of successes and the two numbers of failures are all at least 5. So these actually are like that, the 55, that is N1 times P1 hat, or I guess NM, if you want to use like for M for men and W for women. So NM times PM hat, it would be the 55, right? Because you could say, well, the number of men is 160, the sample proportion is 55 over 160, but then 160 times 55 over 160 is just 55. Right, because the 160s would cancel out. And it's easier just to pull them out of the table and just go, yeah, the 55, that's one number of successes, the 60 is the other one, and then the 105 and the 132 are the numbers of failures. So I think that's easier. But then if we're going to use StatCrunch to get a 99% confidence interval, so I guess just be aware of that, because that's not the default setting, so we're going to have to make that adjustment. And we're going to estimate the difference of proportions of men and women who often have nightmares. So in other words, we're trying to estimate P sub M minus P sub W, if we're going to use M for men and W for women. Okay, so I guess then we're going to have, for the men, we've got, and this, so I guess this is what we're going to need for StatCrunch. And actually, StatCrunch doesn't specify that. Right, StatCrunch just says sample 1, sample 2. So I'll write it to make this look like it's in StatCrunch. So then for sample 1, because the order that we're going in, we're doing it as men minus women. So we're going to put sample 1 as the one that you'd start with in the subtraction. So that should be the men. So then the number of successes should be 55. And then the number of observations is going to be 160. And then in sample 2, then we're going to have the number of successes equal to 60, and then the number of observations equal to 192. And then the other thing is we're going to have to change the confidence level, right? So the confidence level needs to be 0.99 since it's 99% confidence, not 95%. So if we go to StatCrunch, then if we're here, so let's see, first sample is 55 over 160, then the next one is 60 over 192, and then we want a confidence interval, and our confidence level should be 0.99, and then compute. And then we get our endpoints out at the very end, right? So the lower limit's negative 0.098 to 3 places, and then the upper limit is 0.161. All right. So then I guess I can put that in down here. So the 99% confidence interval for PM minus PW ends up being the interval from negative 0.098 to positive 0.161. All right, then at this confidence level, is it reasonable to conclude that the population proportions are different? All right, so usually this is the kind of thing you end up doing with the confidence intervals, like just to see, is there evidence of a difference here? Well, the thing that you would have to look for is if 0 is in the interval or not, because the value of 0 that's what would happen if you subtracted and they were the same number, right? You subtract one number from itself, you're going to get 0. So if 0 is a plausible value for the difference in population proportions, then you can't conclude that they're different. You don't have enough evidence. And it's going to be a plausible value if it's in the interval, right? So we can say here it's no, because 0 is certainly in that interval, right? If you have a negative endpoint and a positive endpoint, 0's got to be in between them. So no, because 0 is a plausible value for PM minus PW, since it is contained in the confidence interval. I guess I have to write confidence interval as CI because I certainly don't have enough space to write confidence interval over there. So why is that the thing that you would look for? Because if 0, and I guess I'll put this part in parentheses, is a plausible value for PM minus PW, then it's plausible that PM equals PW, right? And that's just a different phrasing of the exact same thing, right? PM minus PW being equal to 0 is the same as PM being equal to PW. So in order to say yes, and I guess I can put that in here too, because generally this is a thing that kind of carries through the rest of this chapter. So to say yes, we would need the confidence interval to be either entirely negative or entirely positive, because those are the situations that wouldn't contain 0. So either entirely negative or entirely positive. That N does not look great. And that didn't help. It's clear what word that is. I'll leave it alone. I keep making it worse. All right, so that's generally the idea. If you're trying to see, like, from your confidence interval, would you be able to conclude that the population proportions are different? In order to do that, you need 0 to not be in there. So here it didn't work because we have one negative endpoint, one positive endpoint. 0 is definitely in there. So if 0 is in there, it's plausible that they're the same, right? So you can't reject that idea. D, I wrote this out already. If you want to grind it out by hand, right, this is what the substitution would look like. And then I simplified the point estimate to 0.03125, and then I simplified the entire margin of error in one shot in the calculator. And the way I did it was I did all the stuff under the radical, then the square root of whatever that was, and then multiplied by 2.576. And you do get the same thing. So if you want to do it the long way, you can. I don't know that there's necessarily a lot of virtue in it. I mean, it's nice, but the most important thing, I think, is really just being able to interpret at the end, right? Like, to be able to say, we can't conclude that the population proportions are different because 0 is inside the interval. Like, that's the big thing. If you want to do the algebra, you can, but it's long, because those roots are so big, right? Like those standard errors that you're going to get. And the hypothesis test is actually going to work like that too. Speaking of which, here's a hypothesis test. Let's see. And I got this from a book. I don't remember what kind of book, though. It was like maybe an agriculture book. That would make sense considering the subject matter. So 2 kinds of pairs, Bartlett pairs and Lacani pairs. And then we have a sample of each. And we're trying to see if they spoil, or I guess if they're spoiling at the same rate. So 11 out of the 250 Bartlett pairs had gone bad. 18 out of the 300 Lacani pairs had gone bad. So do the sample data indicate a difference? So, right, just a difference. No specific direction, not do they indicate that Lacani pairs are going bad at a higher rate or anything like that. It's just, are they not the same? Right? That's all we're looking for. Okay, so then the null and alternative hypotheses. I guess you could write them a couple of different ways, but we know we're just looking for a difference. So no specified direction, we need a not equal to in the alternative. So I guess if we just did it with 1s and 2s, you could write it as where the alternative is P1 not equal to P2, and then the null would be that P1 equals P2. Or if you prefer the phrasing with the zeros in it, like P1 minus P2 equals 0 for the null, and P1 minus P2 is not equal to 0 for the alternative, that's equivalent. Like, that would still work. The other way to do it, and I guess if you were going to use StatCrunch to do it, it's just going to have 1s and 2s. Writing them out by hand, I like to use like little descriptors in the subscripts if I can. So you wouldn't have to do anything like this, but the way that I would probably write it is like this. So where the null is PB equals PL for Bartlett and Lacani, and then the alternative is PB is not equal to PL. Because the way that I look at it, like if I was going to do it by hand, if I use the B and the L, then I can't forget which is which. Right? Like I don't have to think like, okay, which one was 1, which one was 2. Like if it's B and L, I know which ones they are. But that's usually not a problem anyway, right? I mean, if you just kind of follow the order they show up in the wording and go, the first one that shows up is a 1, second one that shows up is a 2. And if you always just kind of do it consistently like that, then you'll know which one's which, right? And I think that's probably a good strategy. But then if we're going to use StatCrunch to get the p-value, all right, so all we're really going to need here would be our sample proportions. So from sample 1, which I guess would be the Bartlett pairs, it's going to be 11 out of 250. That's our sample proportion. And then for sample 2, for the Lacani pairs, it's 18 out of 300. All right, and then if we go to StatCrunch, let's see, get rid of that one, get a new one. So stat, proportion stats, 2 sample with summary. All right, first sample was 11 out of 250. Second is 18 out of 300. And then for the hypothesis test, we're good to go here, right? Because the alternative is two-sided, so we're all set. So if we just go right to compute, there we go, right? The p-value is 0.4031. All right, so there's that. So I guess I can put this on another color. So actually going into StatCrunch, what we got was that the p-value was 0.4031, which is pretty big. And then alpha is up here, 0.05. So the p-value is definitely bigger. And so that means that we are not going to be able to reject the null. Right, so 0.4031 is bigger than 0.05. So the p-value is bigger than alpha, and that's the case where the null should not be rejected. Right, so just like before, you can reject the null if the p-value is less than alpha, but that's certainly not happening here. The p-value is way, way bigger. So formal conclusion, these tend to be long when you have 2 samples. In a way, I should have written this out in advance. But I guess you'd say that there is insufficient evidence or not enough evidence to conclude what is in the alternative. So I'll say there is insufficient evidence to conclude, and then this part's going to be really long. So let's see, that the proportion of Bartlett pairs that have gone bad is different than the proportion of Lacani pairs that have gone bad. So the proportion of Lacani pairs that have gone bad. That's a lot of words, right? I mean, in symbols, I guess you could say there's insufficient evidence to conclude that P1 is not equal to P2. Or there's insufficient evidence to conclude that PB is not equal to PL. But PB and PL in words, they're long, right? Respectively, right? PB is the proportion of Bartlett pairs that have gone bad. PL is the proportion of Lacani pairs that have gone bad. So thankfully, if you have to pick out a conclusion, you're just picking one out of a lineup. You don't actually have to write the whole thing out by hand like I just did. But if you were going to do all the work by hand instead of by StatCrunch, I kind of wrote that out in Part E. So you have to get the pooled sample proportion because you need that for the standard error in the denominator of the test statistic. So I just took the two sample proportions, added the numerators together, added the denominators together. So it's 29 over 550 when you do that, which is about 0.0527. Then you can see the 0.0527s in the standard error, so in that root. And then the difference in sample proportions, it's 0.044 and 0.06. So the 0.044 is the 11 over 250, and the 0.06 is the 18 over 300. If you simplify this thing down, you end up with negative 0.836 for a test statistic, and you get a p-value that's basically the same thing. I mean, it's slightly different because I had to round the pooled sample proportion very slightly. So that's why it's off by 1/10,000th, and it's 4032 instead of 4031. But, you know, same conclusion, right? I mean, it's still way bigger than 0.05, and you're not going to be able to reject the null. And I guess you'd have to use StatCrunch here probably, or a calculator, where then you just go to the standard normal distribution and use 0.836 as a cutoff, or negative 0.836. So, I mean, I guess I can actually go through it real quick. Right? It would be calculators, then normal, and then, let's say, I guess you could do it as a between, right? And then say negative 0.836 to 0.836. And then it's going to be 1 minus that, right? Because the red part is what you don't want. So yeah, 1 minus 0.5968 is going to be 0.4032. So that's where that number's coming from. All right. Then let's see. The last thing is, what if you made a decision about the null hypothesis using a confidence interval? So I stuck another p-value 1 in here, but then that's mostly what this next page is about. All right. So first things first, I guess. First sample proportion. So from the first supplier, we have that P1 hat is 26 over 400, right? 26 defective out of 400 bricks total. Second supplier, it's 33 out of 300 that were defective. So P2 hat is 33 over 300. And then notice this time our alternative does not have a not equal to. Right? We're trying to see if the proportion of defective bricks is higher with the second supplier. Okay, well then we're going to have to make that adjustment when we actually go in and use StatCrunch. So if we go to StatCrunch, so stat, proportion stats to sample with summary. All right, so then the first sample was 26 out of 400. The second one was 33 out of 300. And then with the hypothesis test, we want a less than. So you just have to make that change and then compute. And there we go. So our p-value is 0.017. All right. So then when we actually went ahead and used StatCrunch, then we got a p-value of 0.017. And it's the usual alpha. You can see it right there. Alpha is going to be 0.05. So then in the step where we make the decision, 0.017 is less than 0.05. So the p-value is less than alpha, which means that the null should be rejected. Okay, not too bad, right? About the same as before. We just had to be careful and make sure that we changed the inequality in the alternative hypothesis when we were using StatCrunch. All right, then this part, because in several of the homework questions, they have you do the hypothesis test with the p-value, but then there's a follow-up where you also do it with a confidence interval. This is much more direct when you have a two-sided alternative than a one-sided alternative. The one-sided is a little bit weird, and that's really why I wanted to go through this. So basically what you do, like the general idea is you try to match up the confidence level with the significance level, so with your alpha. And then as long as you're using the right confidence level, then basically the way it works is if the null value is outside the confidence interval, then it's not a plausible value and you'd reject it. If it's inside the confidence interval, it is a plausible value and then you don't reject it. So if you have a two-sided alternative, this works out really well because then it's just 1 minus alpha. Right? So if alpha is 0.05, use a 95% confidence interval. If alpha is 0.01, you use a 99% confidence interval. And that's pretty much it. And then if 0, which would be your null value, is outside of the confidence interval, like whichever one is correct for that situation, then you'd reject the null. And then if 0 is in it, then you would not reject the null. The weird part is this last bullet point, and specifically it's this. If you have a one-sided alternative, then the correct confidence interval, or I guess the correct confidence level, right? That should say level, not interval. It looks weird. So the correct confidence level is 1 minus 2 alpha. And that's because basically you have to match up the tail size. So like with the two-sided alternative, like if you were going to use a rejection region, how you would break alpha in half. But if you had a one-sided alternative, you would just throw the whole thing into one tail. It's based off of that. And I kind of mentioned that down here in parentheses. If you're going to use the rejection region approach, then you'd have a right tail with the area 0.01. So like if this is the rejection region, this is actually what these bell curves are for, so I can draw this thing. So then you'd have 0 in the middle, and wherever that is, like whatever critical value we've got right there, then, and I guess I made the tail too big, considering how small that actually is. It's supposed to be 0.01. That's way bigger than 1% of that curve, but that's the idea, right? You'd have 0.01 all in the right tail, because you got a greater than, right? You just shove the whole thing in the right tail. So then if you were going to get a critical value for a 98% confidence interval, the tail size actually matches, because then, let's see, you'd still have the 0 in the middle, and you'd want a 0.98 in the middle for 98% confidence. So then if you have a 0.98 there, then you'd have 0.01 in each tail, like the 0.01 in the right tail in the other picture. So that's why they don't match up exactly with the one-sided alternative. So if alpha was 0.01, it would be 98% confidence, right? Which is 1 minus 2 times 0.01. And I think when this shows up in the homework, they tell you the right confidence level to use anyway in every problem except for one. I think there's one of them where it doesn't specify it, but the rest of them will say, it's one-sided, so use 98% confidence, or it's one-sided and alpha's 0.05, so use 90% confidence. Like, they'll tell you in all but one, but there is one where you do have to figure it out. So then for the test at the top of the page, for that one, alpha is 0.05. So it's where alpha is 0.05, and it's a one-sided test. So then the confidence level is going to be 1 minus 2 alpha, which here would be 1 minus 2 times 0.05. So that's 1 minus 0.1, which would be 0.9. So it should be a 90% confidence interval. Right, so 0.9 or 90%. And then if we went ahead and got it, so we can use StatCrunch to do this if we want to get a 90% confidence interval. Let's see. So the data should already be in it. So if I just go to Options and Edit, then let's say I don't want the hypothesis test now. I want a confidence interval, and I want a confidence level of 0.9. There. So it looks like we have at least round to 3 places, negative 0.081 to negative 0.009. All right. So negative 0.081 to negative 0.009. All right. And then the way that you would handle it now, if you were going to use the confidence interval to make a decision about the null, you'd say, well, is 0 in there? Nope, because both endpoints are negative, so the whole interval's got to be negative. 0 is not in there. So the confidence interval does not include 0, so then you would reject the null. All right, so this note at the bottom, this isn't really a thing you have to worry about, but it felt incomplete if I didn't mention it. The two standard errors are slightly different, right? Just like they are for a single proportion. Like for a single proportion, the standard error that you have for a confidence interval and the one that you have for a hypothesis test are slightly different. So that also happens here, right? Because with the confidence interval, you use the individual sample proportions, and for the hypothesis test, you use the pooled one. So it's theoretically possible to get a different conclusion, but that's extremely rare, and it's not a thing that you have to worry about. You would have to have one where, like the p-value would have to be like right on the precipice. Like if alpha was 0.05 and your p-value is like 0.049997, then yeah, okay, fine. Maybe if you did it the other way, then you're going to end up with a confidence interval that barely contains 0, like it just gets inside one of the endpoints. But that's a very rare occurrence, and you don't have to worry about it. But it felt weird if I didn't mention it, so I threw it in there at the end.